Hey folks, uh, so the last time I was streaming, I was talking about the map generation and the algorithms I would most probably use. And by the way, as always, you can access the live version of my development build following the link in the top left. The link is only active while I'm streaming, so if you want to watch me code live and debug, you can always go to Twitch and run the application while it is baking. Otherwise, you can follow the link I will post under this video to the latest sort of like semi-working build where the game can be tried, essentially. With that being said, I can start the code, and today I will go through my solution and we will see what I came up with during the last couple of days. Now I'm running the game currently, and basically I turned off the logic that would render the actual game, like in the main file, and instead I am running the map class. Now it all starts with setting some variables here, and the most important that we can start with is the width and the height of the map, and then we have some padding. Those are pretty self-explanatory, and like I was describing in the last session, essentially I start with a list of triangles, that is using the delanuator, which my friend wrote. I'm linking his repository in the comments, in the description on YouTube as well. And I talked a little bit about it yesterday, and today we are going to make it into a map, finally. And so the first thing that we want to do is I'm going to turn off the edge rendering. And now we can see the base mesh. And everything in the map is procedural, which means that every playthrough is going to be unique, which is what I am after. Now, the way, if we go to the function that so this is like the first thing is just setting up the canvas and getting the canvas, the 2D context, not the WebGL context, because some things I am drawing in the 2D canvas, and then I'm using the canvas as a source for the texture I will later on feed into Pixie and render within the game as a render target, essentially. It's just very simple to do, and I'm not worried about performance too much at this point, because we're just hacking stuff together to make the game work and to get a feeling, and then we optimize later. So the first thing that we see is this function. It's the mesh. So we are using the delanuator. We are giving it all the parameters it would need, and one of the things that it wants, if we go to the constructor function, after we're done with the canvas, this thing, we get the boundary, because we want to determine the kind of the bounds that are going to be converted and delineated into a list of triangles. And basically this is what it looks like. It's just 4 points, and then I perform some operations on top of those points. So let's see how this works. So these are just 4 simple points, one for each corner of the rectangle. Then I apply a so-called Chaikin smooth, which is an algorithm to kind of go over the list of vertices and then average the coordinates of the pairs of vertices, making essentially a smooth version of the polyline you give it. And then this is a bit silly. I apply the function 2 times to kind of get like twice the smoothing, and like of course like I should have just added the parameter to iterate several times. It's just I've done so many things. This was the last on my list, but it will probably something we will fix. It's not, granted, it's not that difficult to do. So we do the boundary, right? We smooth it out, and then because I also want the map to be kind of noisy on the edges, I don't want the map to be a perfect, like nearly perfect ellipse every time we play. So for that reason, the solution I came up with is basically go through each of the points on the boundary, and maybe I can render the boundary instead. Yes. Well, the lines are not close, but that doesn't matter. Maybe I can do render points. And I hope this works. Yes, the points are too great. Okay, now we see the points. Great. And then for each of these points, I kind of get, let's see where this piece of code is. So for each of the points at the center, like at each point, I place a circle with a random radius, 30 to 60 units. And then I say I want to have 5 vertices on each of the circles. So it's essentially going to be exploded a little bit. And then after we do that, we get this result, right? So it's just a bunch of circles. Now the next thing I use is a polygon generation on top of this. So if I go to the good old Paint, I can illustrate. So basically there are different methods to convert a point cloud of this sort into a polygon. One method would be to making a convex hole, and it would be something like this. So it would basically try to make a convex shape out of it, something like this. And another way we could do it is by making a concave mesh. Now the difference is, of course, if we have a convex mesh, so let's say we have a set of points like so, and we have like a cavity in the middle. So the convex mesh would be something like this, and I'm drawing it very roughly, of course. And the concave mesh would be something like this. Essentially, we want to have this sort of holes in it. And I always used to like misname these two types of meshes. But basically, if you have a cave in it, then it's a concave shape. And if you don't have a cave in it, then it's a convex shape, essentially. But these are very schematic drawings. Take them with a pinch of salt. And so basically what I want to do is to have a concave mesh, because I think it looks nicer. It can like create this sort of like a little islands instead of having like a blob. And for that thing, I'm not writing the code myself. I use the extension called Concave Man, which is surprisingly efficient, and it's very nice documented. And yeah, it just seemed like a cool thing to use for free, which I am always for. And then next, when we apply the concavity, and there is some, like, they have a different way of naming points and stuff, so I have to do a little bit of converting from an object to an array of coordinates, and then from array back to an object. It's not beautiful, but I don't want to rewrite everything just because we have a little bit of an API difference. Now, after we do that, if we render it as points, we still see the points, but now we don't see the inner points anymore. Which means that we have generated a sorted list of points in a clockwise or counterclockwise direction. Because when we describe a polygon, we want the dots to be ordered. They can't just be randomly placed. And so that's what the algorithm does. It picks out the dots that are sorted and end up in a concave shape. So now that we have that thing going, let me go back and fix this stuff up. Okay. So that thing, the boundary is being fed into the delanuator. So this is our boundary. We don't care about the Voronoi areas for now. This is our boundary. And then we use the setup mesh function to call the delanuator and generate some metadata for us that we will use later. And namely, the delanuator gives us a mesh, gives us a list of edges and list of loops, etc. Now, the next thing is that we are kind of rendering the edges now. So this is what it came up with. And we can configure the scale of the point cloud within, so that we could get like different amount of nodes. Through trial and error, I found that like this is way too much stuff happening. So I kind of arrived at number 25, which I think works the best for my purposes. This is enough stuff for a game for now that we have in mind. So that is that. And let me return this back to normal. Now we have this irregular boundary that is being fed into the delanuator. The delanuator provides us with a grid. And what we do next is we convert the list of connected edges into a graph. So basically, right now, it's just basically sorted edges and separate triangles and a list of vertices, list of coordinates, x and y coordinates. So the delanuator I am working with, that my friend wrote, has this performance thing within, where instead of having an array of x, y vertices, instead we have an array of numbers, essentially. x, y, x, y, x, y. So if we want to find a point, we need to find the index of an x and then add 1 to it. And it's essentially like works like pointers. So with all of that in mind, we want to iterate over the list of edges that the delineator gives, and then see which edges, list of triangles, and then see what those are connected to, which edges are connected to which edges. And for graphing purposes, again, I did not write the graph myself. I just used a dependency, which is much faster, and it has been proven to work efficiently. So it sounds like a good deal to me, because we are not scientists, we are game developers. So we spend time on games instead of writing complicated algorithms. Unless the game is about an algorithm, then I think that makes sense. It's justifiable. Or if we get like very crappy performance, then it's time to get our hands dirty. But for now, it seems like all is good. And now when we set up the graph, we are basically iterating through the list of points, and we add each of the points in the graph as a separate node. So each one of these points, vertices, would end up being a node, and then we go through the list of edges. We see which point is connected to which point, and we create links between the nodes. And after that, also each node has an XY position, of course, because it's a coordinate, but also I'm applying a cost, because we are going to use the graph for a pathfinding algorithm. And it's nice to know if some nodes are costlier than others, because then it means that a straight line is never the shortest path you can take, which is a very nice thing for organic looking terrains and roads. Now, this is where we apply the noise, and we use a Perlin noise for that, and then we query a certain point on that noise. It's exactly the same thing that is happening in the terrain abstraction in the game, where we place like different grasses, like pebbles, grass patches, trees, and stuff like that, and generating the map, of course. So it's exactly the same implementation and the same usage. And when we do that, let us see. After we have done that, we have our graph. Now the next thing we want, now, like, essentially, if I am to illustrate this, essentially what we have is we have all of these separate nodes, and all the nodes are connected, all the vertices are interconnected. So this means that if I, for example, start at this vertex and I need to get to this vertex, I just need to query basically all the surrounding vertices and see if they get me closer to my goal, and then I find a path that actually gets me to to my goal. So it would be like this edge 1 and this edge 2, and this would compose our path. Like if we call the points A, B, C, so the path would be A, B, and C nodes, which is exactly what we need. So that's why we have been connecting all the dots and stuff. Now that we have done that, we can go and see the goals function. And the goals is essentially just a pick of different, is like a selection of different points on the graph that I would like to get connected. So basically something like this, right? And based on the points that we select, we would get different patterns emerging later on. And what I'm doing now, like the next thing that is very important, because in the game, I currently want to have 4 different zones with different like properties. And to determine those zones, that's why before doing any of this, I have created a Voronoi diagram based on a random set of points. And we can preview that stuff here. So basically every time we start, every time we generate the world, we end up having this like 4 zones generated randomly, and we are guaranteed to have our map have nodes, at least one node in one of each zones due to the placement of the points. Now the way Voronoi map works is basically I went through it in the last video, but basically we have this cells, and we end up like finding like we end up growing the cells and then finding where those cells are stopped by growth of other cells in a very simple nutshell. And this is a nice illustration. So this is how the algorithm works underneath. So that's what I do. I pick a random number of, like not a random, I pick 4 points for each of the zones. I place them kind of in the middle, and then I run the Voronoi algorithm, and then I get the diagram like this. And now I can like query the diagram for each of these polygons. I can query, hey, is the dot I have in my hands intersecting with this polygon? Which cell is it intersecting with? Which cell is it contained in? And then I can pick, like sample the properties of that cell in the Voronoi map to get like to do some game stuff, to spawn different enemies and stuff like that. So that's the Voronoi map. And now when I'm creating the goals, I try to make sure that I pick one vertex in each of the zones, so that I have some game stuff to do. So there are some roads that lead to each of the zones, and I collect those goals, and then I also add 2 additional goals, like which is at the 0 of the path, which is going to be around here, and at the end, which is going to be around here, so that we have the entire map at least covered once to occupy as much space as possible. And then I also, like after setting up the goals that I will use, I'm also mapping the direction. So for example, from goal number 0 to goal number 1, that's one connection. Then from from the red cell to the yellow cell, it's going to be one connection. From the red cell to green cell, there is going to be a connection between those 2 goals. From yellow cell to blue cell, and etc. So I take all of the combinations, plus I add the 2 goals. I connect 2 goals from the beginning to the end of the boundary, essentially. from the beginning to the middle of the boundary, because boundary ends in the beginning, because it's like circular, like topologically circular. Now that I've got the goals and the directions, the next thing is to set up the paths, which is the meat of this entire endeavor. Now, we get, so to do that, we get our graph and our nodes, the goals, the direction, and some colors. And we go into the setup paths function. And basically, to do path finding, you want to have two functions. They are called the G function and H function, which basically determine how you perform, like how costly it is to navigate the terrain and how you navigate that terrain. And then we have basically a map over all of the different connections from point A, point B, point B, point C, point A, etc. So we take those nodes, we give it to the Pathfinder, which I also didn't write myself. It's a library on npm, so it's all very simple. You just plug and play. I place the two different goals. I get a path, which is an array of nodes. And next, like after I've done that, since I've picked the path, let's say, let me illustrate. After I've picked the path, for example, it might look something like this. From this point to this point. I make sure to go through all of these vertices and increase their cost to kind of make the algorithm try and not pick them whenever possible, so that we don't end up having like same paths used for nearly identical set pair of goals. So then, because the cost of this path is higher in general, it is going to kind of use like something else. So that is kind of like that, and then we have the polyline for the path, and we can illustrate what's happening. So let's see. We have the polyline. What do we do with the polyline? We put it to map path. So this is map path. And then, okay. So it means that if I go to the rendering section, and then let's see if I can render this stuff. I want the color black, and do we see something? Let me turn this off. Okay, we don't see anything because, okay, now we see. So basically we end up having like all of these different nodes connected via a path tracing algorithm, and they are also smoothed out, which I did not intend for the why is it smoothed out? Am I doing something? Oh, this should be, I'm querying another thing. So I should be doing this. Let's see. Oh, it's just too much stuff, and like it's kind of a bit too much. Let's see, where is this thing happening? So let me first of all collapse all of this stuff. We don't need it, it's just confusing. Okay, so we do the path graph for which, okay, we are creating the, let's see. Okay, we are drawing the roads. What are the roads? This is the result of this. Okay, so we're back here. Who is touching the roads? Okay, that's where we do the smoothing. So if we remove this stuff, we end up having basically the nodes over the grid that we have connected via path tracing. And these are all the goals that we had. Now, let's see. If I just, for the sake of example, if in my okay, goals, edge goals, and then, so if I do this, we will only have 2 points connected. So this is an example of just having 2 goals connected to each other with all of this noisy cost type of this system, and this is what it looks like. And then like it fills up more parts of the map, and we still get some overlap between passes, but that's why we that's what we are fixing next. So if I apply random colors to each of the roads, I think this works. Yes. So we can see that some parts of the map, like for example here, we can see that there is an orange path coming through here, and it's kind of like overlapped with the blue path. So that's not what we want in the end, because at one point on the ground, there could be only one path. It doesn't make sense to have like overlaying paths. So that's what we are fixing next. And after we have like our separate array of different paths, next thing we are doing is, okay, the next thing we are doing, oh, let's see. Man, I don't even remember where I'm fixing each of the things. I think while we are in the path function, let's see. Yes. So the path function outputs several things, right? It outputs the roads, which are the separate roads. It outputs the road graph, and then it outputs the road nodes. Now, this is just an array of different splines, and this describes the graph. Now, the graph, when it is described by a graph, the graphing of it and adding the nodes and adding the links is done by querying the distances of each of the points. So when we let me illustrate this. When we make everything nice and make everything smooth, you see like all the different lines have different colors. But if we are to render the road nodes, I don't think it will be visible. Oh no, it actually is. It actually is. Let me try to zoom in on this stuff, and then so basically, I am downsampling each of the lines, and then for each of the points that I ended up having, I go and for each of the splines. So I pick one spline, I pick the first spline, and then I say, okay, add this entire downsample spline to the graph. And after I've done that, I take the next spline. And for each of the points in the spline, I ask, hey, are you close enough to any of the points we have in the graph already, to any of the nodes? If not, you add yourself. If you are close enough, then make sure to merge to whatever thing it is you are close to, and you use that node instead. And so I repeat that process for each of the vertices on each of the separate paths by ending up having a graph without overlaying vertices and without overlaying nodes. Like here, for example, you see this connection, when it was like different paths, ended up being like this sort of connection. So that way we kind of like merge things together while reconnecting the new set of unconnected splines into a single graph. So that's where we fixed that issue. And why do we do that? Because we want to have one graph, because we are going to do fast travel. We need to know exactly where we are on the map at all times and where it is that we want to go. And that way, we will be able to run the pathfinding algorithm now on this newly generated graph. That's all good and dandy. Now that we have all of this prerequisites, we there are many different like ideas I had about this, but I found that this works good enough, so I'm not gonna like touch it until I have a need to do so. And these are the clusters. Let me illustrate what I mean by this. If I even can illustrate, maybe I should disable this stuff. Okay, now we see this additional random like dots with different colors. Maybe if I convert like the background, yes, this is better. So basically all of the nodes on the original nav mesh, on the original graph that are free, all the vertices, I mark them. I get a list of free vertices. After I get a list of free vertices, which is in this function, the clusters, after I get a list of free vertices, I take all of this I take all of these vertices, and they're like one group of vertices, just a plain old array. After that, I take it in and I perform clusterization by distance, which is basically groups together things that are like close together, so that groups that are like at a higher distance from each other, they end up being separate. So then we have a list of these points, a list of lists of points, and these are different clusters. And why do we need that? We need that because after we are done with the clusters, we convert the cluster point clouds into concave meshes. And basically, if I am going to illustrate this, we get this thing on top. So each of the clusters is getting wrapped with edges. And so we have this separate holes. And we can use the holes like for different reasons. These are not very useful, but if we smooth them out, let's see, holes, set up paths, we don't need this, set up holes. Yeah, so basically after we perform some smoothing and then some downsampling and some smoothing again to like achieve a nicer result, we end up with having this thing instead, which now look like islands. They're much nicer to look at. They're more organic, and they can be used as guides to trace lines on the map later on. And so this thing looks pretty nice already, but we're not finished yet. So I am going to show both. Okay, so now we have the concave polygons and the smooth versions of those concave polygons. Now that we have done this, the next thing, let's see what comes up next. So we have the hulls. Next thing, because usually when we look at like really ancient, like, or medieval, this kind of like looking maps, we have oh my god, why is it so difficult to open a picture? So we have this different like decorational assets scattered around, and to place the assets on our map, we need to make sure the assets are not interfering with the important features, with landmarks and with roads and stuff. So to make that to make sure that never happens, this is the solution I came up with. And of course, like as everything else, I don't know most of the time what I'm doing, and I don't know how efficient it is. Maybe, you know, there is something out there that would make everything run much better or faster or be more maintainable. But I do, you know, I do stuff to the best of my abilities, and I learn along the way. So for now, my solution was to, let's say we have like some sort of a polygon. Now my solution was, first of all, fill the polygon with dots. Then from each of the dots, I try to place a circle starting from 0, and I basically go in steps, and I try to place a circle until the circle kind of intersects the edges of the polygon. If it intersects, then I stop. So I end up like having a bunch of the circles from all of these dots that are inside of the concave polygons, and I have like this kind of a mess. And let me illustrate that. Let's see if I can do that. Do we have generate circles, fill concave, no colliding circles? So I think if I return this, and if I also render the circle points, yes. So now we see there is like, for each of this concave polygons, we have like a bunch of circles that are filling them in. Now the next thing, I want to remove the overlapping. So I just sort the circles from like by radius, and highest in the beginning, lowest in the end, and then I start picking circles from I take the first circle, the biggest one, and then I pick the next circle that is not intersecting with it, and then I go on and on and on, and so on and so forth. So that way, if I return the non-colliding circles, I end up with this nice looking circles that leave like almost exactly, it's all about like the step precision, and they live inside of these islands. So there are sometimes there are precision errors, but that is fine. Like we don't really care about those. And this thing is needed to place assets later on, which brings me by the way, to fill a concave polygon with dots, I found like a very neat method. I don't know exactly how efficient it is. It's basically scanline. So you start generating line. Let me see if I can actually make that happen and alter some code here. Let's see. There's like a bunch of functions that call each other, and scatter points. Let's see, circles, points, map. So first of all, the scatter points, I have a jitter amount. So I'm going to put the jitter amount to 0. So that's the first thing. And then when I fit the circles, I place the radius at 0. And then I also want to remove this thing. And then we would be able to see the scan lines, hopefully. If nothing breaks. I think the 0 radius kind of freaks it out. Fit circle into concave polygon. So we can just probably comment this out and then see if this stuff works. Yeah, I think like the 0 radius is freaking it out. But what I can do instead, I don't need to touch this stuff. Let's see, I'm gonna remove this as is. I'm going to oh, maybe I should do this. And then I am going to go back to the map and instead in this function generate circle, I put the radius here for illustration purposes and hopefully that would work. It doesn't. Let's see. Well, such is life. Let's see what exactly is wrong. I'm going to bring it back to a working state. And then hopefully we go from there. Okay. 6:15. Where exactly is... We don't even have that much stuff. What are you talking about, man? Let's see. Can I... No. Well, okay, we just... Oh no, it's here. It's here. Okay. Well, that's fine. Okay. It doesn't like the... Is it not jitter? Oh, that's resolution. That's not jitter. Yeah, that makes sense. Okay. Okay. And then... So the resolution, if I put it to 1... let's see. Okay. And then... okay, if we go... Where is this stuff? Just make sure there is something there. Okay, I see some things happening, which is a good sign. Now, if I go back to the mass library, what do we have here? Scatter points within a concave polygon. Okay, so we have a padding, a jitter, do we use it here? This is just the other function. Okay, so we are going here, hull circles and hull points and circle points. We want to make sure we are exactly rendering. Yes, we are rendering that. So that part is fine. And this means that all we need to do is fix this thing. So we have the polygon, we have the resolution, and then we are doing fit circle. I suspect like the crap is happening here. So what if I do this now that it should work? Yeah, it's perfect. And now all we want to do is to adjust the resolution. Finally, I can make it. Yeah, so exactly. Maybe resolution 5. So basically, this is what we do. We can also remove the padding for illustration purposes, which makes it... Yeah, so basically, you start scanning. like with vertical or horizontal lines, and then you identify the points of intersection with the polygon, and then you fill in the dots within those points of intersection, and you do it horizontally and vertically. And you end up with having like a bunch of points. And you can also like adjust the padding so that we don't interfere with the edges that much. So we kind of do this, and then we can apply some jitter, like to make them a bit more random and stuff. So this is like a good way that I found to fill the points in that I would later use to spawn the circles and grow them until they hit the boundaries of the concave polygon. So let me bring this stuff back together and try to make sure I didn't break anything while playing around with this stuff. Okay, do we get the circle points back? Yeah, we got our sorted circles, which is very cool. And then I just add some random points to the map, to the edges as well. Sorry, to the concave polygons, like just to like put in some dots on the map. Little dots look nice in this doodly style. And essentially, this is the map, right? And then what else do we have? Oh, this is just the boundary. So yeah, basically this is what we have. And now to illustrate the actual path tracing. So this is all of our crap. And now we illustrate path tracing. And we do that by picking, so basically I wrote a little function to set an interval and to pick like a starting position of 0, a node at 0, and like it starts adding, incrementing over the rest of the nodes and plotting paths between them. So we can see this tracing function at work here. It would be better. So now let me do the following. I am going to bring this like so. And so we can see this tracing function now working with the final graph that we have, which is exactly what we need for the game. And it looks neat as well. Yeah. Now, after I've done this stuff, I've tried to make it look a bit like gamey. And this is what I did. Let me maybe, you know what, maybe I do this. It's still transparent. That's because I'm not clearing it out. Yeah, let me first clear it out and then we can get this stuff. Yeah, so this is essentially how I want this thing to work in the map, in the game, excluding the assets, because assets we add in Pixie. All right, because it's our WebGL engine. This is just the canvas. Now the next thing, after we have all of this jazz going, the next thing is we add two little utility functions. First, to get the texture for the Pixie, and this is a Pixie texture that we can update whenever we feel like. For example, I'm for now, like for this purposes, I think I am. When am I updating this stuff? Yeah, okay. So the update. Oh yeah. So basically every time in this like set interval function via a callback, this rendering stuff happens, and then the Pixie texture gets updated. This is not something I will do in the production, like in production in game, because I don't need to animate the canvas. I would say like most of the time. So this is just for like testing, and this is fine. And then I have the function to return that texture, because I don't want to recreate the texture. It's the same texture, and I will dispose of it when I'm done at the end of the, well, pretty much when you leave. I don't even need to dispose of it, because like you will get it will get garbage collected when the game closes. And then we get the circles to place our assets in. Now, after that stuff, we can go and turn on the actual game. And when we turn on the game, so basically in the main place where everything is getting like handled, all of the state and stages and stuff and switches, we instantiate this map and we just create this simple cute line, which gives us a map. And after that, we pass it into the level, into the stage, and I currently spawn it in a pause, a menu. And you get the map in the pause component, and then the map is being set up. And for each of the circles that I end up getting from the map, I place some random assets that I have at my disposal at the moment. And yeah, I do some basic state handling and event binding so that it gets shown at the right place and the right time. And I am also going to hide it by default. And then, so this is our game, right? It's like cute and stuff. And then when we go to the pause menu and we press map, we can see the map functioning. And we can also see the different assets kind of placed. And we can even render, since like this is just showing whatever is on canvas, I can render the circles, and we would see the circles, you see? And this is where we are placing the assets. So this is exactly what we wanted from the beginning. And every time I'm going to basically, let's see. I'm going to make it visible true so that we can reload a bunch of times and see different versions. So you see there is a tree now because it was a large enough circles. And I would say 90%, 99% of the times even, like, well, the road is covered here in this case. And like we need some tweaking to do with our like smoothing and stuff like that. But like most of the time, like it looks pretty fine. And basically we can also, by adjusting the number of goals and areas and like the pathfinding algorithm, we can end up at different patterns. For example, if I reduce the scale of the point cloud in the main delaminated mesh, this is what I get. Like it's a whole different feel. It's a whole different type of map. And then we also like have all of this stuff with the no, we don't want this. We want this stuff. Well, transparency does not work properly because like I'm rendering the thing in a semi-transparent way to overlay on top of the scene. But basically, this is what the zones look like. So one of the zones will be a forest, and then it will have the forest themed assets. And then another will be like some other zone, and then it will have those assets. And every time you go from one zone to another, like there is stuff that changes slightly. And I will also need to experiment later on because like as I see now, for example, you see the zone changes when you go, you see, from this level to this level, and then it goes back to not being in that zone again. It's a different zone now. So I'm not sure how exactly that will work out in the gameplay. But I guess those kind of things, like those are like the nitty and gritty, we will have to see as we go. It's very difficult to predict anything at all. Like I don't even know what the game will end up looking like. It's just too much variables and things. So basically, what I am trying to do is kind of just go try to do something and then see what the game wants me to do next, what it feels like doing. And that is kind of, yeah, that's kind of like my process. Let's see what happens if we do point cloud scale 50. Yeah, well, this is a simple, like much topologically simpler map, and we'll see what plays best. So that would be all for today, folks. And I will see you guys next time. Thanks to everyone who was watching on stream. And thanks to everyone who is watching on YouTube. I hope you guys have a nice day, and I will see you next time.